Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hello students, good morning. So in previous few classes we have studied about isomerism. Isomerism, it's two types, structural and stereoisomerism. Structural isomerism we have seen there are few types, four types particularly we have seen, and there are also tautomerism and ring chain isomerism which we have studied as a part of a structural isomerism. Then we studied about the stereoisomerism and two different types of the stereoisomerism we have studied in detail. The geometrical isomerism and as well as the optical isomerism. Optical isomerism, there is symmetrical isomerism. We have studied mostly cis and trans, and if the substituents are all the substituents attached to the hinder bond with the hindered rotation are different, or at least three are different, then we have seen we can use EZ notations and how one can find out the EZ notations based on the CIP rule that we have also seen. We decide or determine the priority of all the substituents that are attached to a given carbon atom, and based on that, if all the substituents bonded to two different carbon atoms having associated with the hindered rotation, if the same periodic substituents are on the same side, it is Z, and if they are opposite side, it is Z. Those things we have seen. And then we have also seen certain properties of geometrical and geometrical isomers. And then we will move to optical isomerism, particularly we studied about the enantiomerism when the and optical activity, rotation of plane of the polarized light. And all these things we have seen optical isomerism particularly shown by asymmetric molecules, and asymmetric molecules having only one carbon as a chiral carbon. If a molecule contains only one carbon atom as a chiral carbon atom, means only one chiral carbon atom is there in a molecule. If in such a case, that molecule shows optical activity, and if it is showing optical activity, it can have two forms: D form or L form. D form is dextrorotatory form or plus form, and L form is levorotatory form. Is the left hand side is anti-clockwise rotation. And D form is clockwise rotation of plane of the polarized light. L form is anti-clockwise rotation of the plane of the polarized light, and so that form is L form, and this D and L form are mirror images of each other, but they are not superimposable. So what we see, the mirror images which are non superimposable are called enantiomers. So enantiom is opposite, so they are opposite, having they turn the plane of polarized light in opposite direction, and that is why they are called enantiomers. And the DL form of the enantiomers. Then we have also seen R and S notations of enantiomers and those things. Let us now move to some fundamental concepts in organic chemistry, which are very important to understand the mechanism of organic reactions. Particularly, what we see that the organic reactions when are performed using certain reagents. And what does it mean? In an organic reaction, we see a carbon atom forms a bond with some other atom. So in an organic reaction, an organic molecule, which are also called substrate, reacts with an appropriate attacking reagent, which leads to the formation of one or more intermediates and finally products. So usually, what does it mean? Usually, organic reactions, not all, but most of the organic reactions happens in multiple steps. So all the steps between the multiple steps and the final step, finally what we get is called product, and the initially what we started with is called reactants, and from the reactants and products there are many steps that happens. So all the mm, different products are at different steps other than the final steps are called intermediate. So what do we see in organic reactions? We see a carbon atom forms a bond with another carbon atom or maybe some other heteroatom. And these organic reactions, this is how we see the organic reactions are performed. So there is an organic molecule which we also call such organic molecules as a substrate, and then there is an attacking reagent which attacks on this organic molecule, and a new bond is formed. In some cases, what do we see? We also see some old bonds are broken, and old bonds are broken, and a new bond is formed. And when this reaction happens in a multiple step, more than one step, so we see also the formation of intermediates, and we also see some side reactions happens, and then side reactions forms byproducts, which are undesirable products. So in organic reactions, we also try to reduce or to minimize the amount of this byproduct. So what do we see? Organic molecules, in the first step, it forms intermediate. Intermediate are not stable molecules or a stable chemical species. They get converted into another intermediate or maybe the product, and the reaction happens in only two steps. So this intermediate will be converted into product. Of if this reaction happens in three, four steps or more steps, so what will happen? This intermediate in presence of some other chemical substance, other reagent will get converted into another intermediate. Then that second intermediate will get converted into some other intermediate by the influence of some other reagent or maybe by the rearrangement of this structure itself. So this is how we finally get the product. So it's what we call substrate. A substrate is an organic molecule usually, or the molecule which forms a bond at least, or which gives carbon atoms for the formation of a new bond, are called substrate. And the reagent are what it, they are usually the heteroatoms, the means chemical species or the reagent containing heteroatoms. They are usually inorganic molecules or inorganic species. So the substrate is the reagent that supplies carbon to the new bond, and the other reactant is called reagent. So suppose there are only two reactants for a carbon for an organic reaction, for an organic reaction. So the reactant which provides carbon atom to the new bond is the substrate, and the other reactant is called the reagent. If you are having, if suppose there is only one, sorry, oh, suppose there are more than two reactants and only one is providing carbon atom to a new bond, then the other reactants are called reagent, and the one which provides the carbon atom to the new bond is called substrate. And what we, as I said earlier, there are also reactions where the carbon-carbon bond formation happens. Like if you look at the aldol reaction or the organocatalyzed Michael addition reaction, there are many such reactions where carbon-carbon Heck reactions, Suzuki reactions are there. Suzuki reactions, the carbon-carbon bond formation happens. And when the carbon-carbon bond formation happens, then how will we decide both the two substrates? They form carbon-carbon bond, means both the substances, both the reactants are provide carbon atom to a new bond. In such a case, the choice is arbitrary. We can choose anyone on which our focus is as a substrate, and then the other one will be called as reagent. So, if the two organic molecules they take part into the reactions, then one we can call one as substrate on which we are focusing on, and another one as a reagent. So, in organic reactions, sorry, in organic reactions, a covalent bond between two carbon atoms or carbon and some other atom is broken and a new bond is formed. And this is what we see. This is in general happens for all kind of chemical reactions. In organic reactions as well, what we see a covalent bond between two carbon atoms or carbon and some other atom, or that means the heteroatom is broken. So old bond is broken, and that this old bond is in the reactant, and this old bond is reactant means mostly will be in the substrate, and a new bond is formed, and this new bond is formed. This new bond may form between two carbon atoms and carbon or heteroatoms. And heteroatoms earlier I have defined heteroatoms could be nitrogen, phosphorus, oxygen, sulfur, or maybe the halogen atoms like fluorine, chlorine, bromine, iodine, etc. Then another terms come the reaction mechanism. So as you know, reaction, this term you are already aware of, and the mechanism, anything if you know the mechanism, the process by which anything is happening is called the mechanism. So if a reaction, if you know the process, how the reaction is happening, that entire process is called reaction mechanism. So understanding how a chemical bond is broken and how a new bond is formed in presence of a reagent or many reagents at a given temperature means in the given conditions, this entire thing is called reaction mechanism. Thus, the reaction mechanism is defined as a sequential account of each step. So, as I said, organic reactions may happen in multiple steps. So, sequential account of each step means in which sequence all the steps are happening, describing details of electron movement and how the electrons are moving from one substance to another substance, or maybe one reactant to another reactant, and also how the energy is required or energetic of the entire reaction, means the energy profile, that what is the barrier associated with each step and what is the amount of the energy that is released or that is absorbed at each stage, the entire thing. So the energetics during bond cleavage and bond formation and the rates of transformation of reactants into products at each step is called reaction mechanism, and the rate of transformation is also called what we study it in the chemical kinetics. So this process called kinetics. So there are two terms associated with organic reactions, so thermodynamics and kinetics. Whatever the needs change in the energy of reactants and products we observe, we find out experimentally, this we call as a thermodynamics of the reaction. And what is the barrier associated with each step of the reaction is called kinetics of the reaction. So these are also two terms which are important for us to understand. Thermodynamics as well as the kinetics. Thermodynamics means the net change in energy of the reactant or the product during of chemical transformation, and this is for the each step and from final initial reaction to the final product as well. This is called thermodynamics. And the kinetics is what the calculation or estimation of barrier associated with each step, and this barrier is what it is nothing but activation energy associated with each step of the reaction. And this what is activation energy, go back to your chemical kinetics class and watch those videos. I hope you will still remember this. So the knowledge of reaction mechanism helps in understanding the reactivity of organic compounds and in planning strategies for their efficient synthesis. What does it mean? Is it true? So what is the use of knowing reaction mechanism? So the use and the benefit of knowing of reaction mechanism is once you know the mechanism, you know the exact role of each reaction. In what step a particular reaction, suppose a reaction you are starting with one substrate and three different reactions, then what each reactant, when each reactant is involved in what step of the reaction and what is its role, what kind of role it is playing, and when it is playing, what is the barrier associated with the reaction. If you know exactly everything, then what you can do, you can also perform similar reaction with some other reactant. So you will obtain different product and which different products means depending on the requirement you will find different material. And not only that, even if you want to enhance this efficiency of this process, of since you know each reactant, how each reactant is performing, maybe you can do a slight change in the structure of the this reactant or reagent. And just a small change in that chemical environment may lead to a very efficient chemical process. So knowing this reaction mechanism is very important for organic chemists to perform reactions in laboratory. And once they know the mechanism, they also design new experiment, and with the new experiments we get new materials. And not only new materials, we can also suppose a reaction is happening in 7 states, and if you know the mechanism, the role of all the reagents, then you know what are the roles and what are the reagents and what properties a reagent can have to make this particular substrate into convert this particular substrate into the product. Then maybe instead of using two different reactants which performs reaction in many steps, you can use a single reactant having all the properties of the three different or two different reactants. So this reaction will happen maybe one or two steps. So if you reduce the number of the steps, the reaction yield will be more. And that is how the knowledge of reaction mechanism is important for not about for anyone who is doing organic chemistry or organic reactions in the laboratory. And also the organic reactions are also these reactions also happen inside our body. So because this is how the organic molecules, they are initially isolated from the living organism, and that is why their name comes the organic molecules. And so our body has many organic molecules, billions or millions of at least the organic reactions happens, different type of reactions happens in our body. So with the knowledge of the mechanism, you also get certain idea about what happens in a different chemical conditions or in the cellular conditions. If a different reactant is there available in the cellular condition, what kind of reactions it will perform, and so this will also help us to find out the drug suitable for a particular disease. So let us now understand about some more terms which are important for us to understand mechanism of an organic reaction. So first, let us study about the fission of a covalent bond. So what we see in organic molecules usually forms covalent bonds, and all the organic molecules mostly form covalent bonds. If the bond is not covalent, or even if it contains carbon, usually those molecules are inorganic molecules. So organic molecules are they contain covalent bonds, and these covalent bonds during a chemical transformation may be broken, may be cleaved, and there are two kind of cleavage by which a covalent bond of a substrate can be broken, or maybe the reagent may be broken. So a covalent bond can get cleaved either by heterolytic cleavage or homolytic cleavage. Heterolytic cleavage means, and then the homolytic. What does it mean? Heterolytic, if we know a covalent, if the covalent bond is there, there will be two electrons that will be shared between two different atoms. And if this shared pair of electrons goes to only one atom during the cleavage, then we call heterolytic cleavage. Means electron is not equally distributed between shared pair of electrons once this bond is broken. So both the electrons are given to one atom and one atom. So the atom which gets both the electrons, shared pair of electrons, will attain a negative charge, and the atom which loses the electrons because it has also shared one electron in the bonding, so that electron has gone to another atom. It means it loses its electron, so it will gain a positive charge. And that is why in the heterolytic cleavage we get two species with charges. One is having positive charge and one is having negative charge. In heterolytic cleavage, it means both the bond pairs goes to only one atom. It is not the equal distribution of the shared pair of electrons. It is so if the equal distribution of the shared pair of electrons happens between the two covalently bonded atoms, then such cleavage or the such breaking of the covalent bond is called homolytic cleavage. Cleavage means the breaking of a covalent bond. Let us study about heterolytic cleavage. The bond breaks in such a way, in the heterolytic cleavage, bond breaks in such a way that the shared pair of electrons remains with one of the fragments or one of the atoms. So if shared pair of electrons, if both the electrons remains, it goes to only one atom, then such cleavage is called heterolytic cleavage. I have just explained. Usually bond pair goes to the more electronegative. This is very important point. Why the bond pair goes to one atom and not to another atom? And this happens if you understand the electronegativity difference between shared pair of electrons. If you share electronegativity difference between the covalently bonded atoms. The two atoms are there and they form a covalent bond. And if there is electronegativity difference between them, what do we see? We see this bond is already polarized and the shared pair of electron is already shifted towards the more electronegative atom. So because of the polarization of this covalent bond, shared pair of electrons is already it is already polarized, it is already bent towards the more electronegative atoms. So in the cleavage, what happens? The shared pair of electrons goes finally it is because it has certain inclination to go towards certain atoms. So it will go towards the more electronegative atom. So this is an important point. The bond pair goes to the more electronegative atom. So if the heterolytic cleavage is, if a bond is given there and if someone asks you to in heterolytic cleavage, which species will attain a negative charge and which will attain a positive charge, then you have to look at both the covalently bonded atoms, and then you will have to understand which one is having more electronegativity. And the atom which is electronegativity is more, it will attain both the electrons, so it will attain a negative charge. So in this case, if you look at this example, the heterolytic cleavage of CH3Br, which is bromomethane, so what do we see? Bromine electronegativity is more than that of the carbon, and so the shared pair of electrons, both the electrons shift towards the bromine, so bromine attains a negative charge, and the CH3, this species, this fragment contains a positive charge, and this is called methyl carbocation because this is a methyl group and it attains a positive charge, so this is cation, and since this cation contains a carbon atom, so it's also called carbocation. So this is carbocation and this is methyl carbocation. Please remember that carbocations are also called carbonium ions. This is old nomenclature, but this it is still in use. And so carbon cations also are also known as carbonium ions. So what we see after heterolysis means heterolytic cleavage, one atom has a sextet of electronic structure and a positive charge. So what do we see? This CH3 group has sextet of electrons. Carbon has only six electrons in its valence shell. So this is called sextet condition. So carbon, it has in this molecule, carbon has 8 electrons, 2 electrons from the sharing. So actually carbon has atom has 4 electrons in its valence shell and 3 electrons this carbon atom get from the sharing from 3 different hydrogen atoms. So 3 more electrons, 7 electrons, and 1 electron it gets from this bromine. So 8 electrons, total electrons become 8. And since out of these 8 electrons, 2 electrons of the shared pair are shifted towards the bromine, and so this carbon will have only 6 electrons in valence shell. Now, another way to understand this is carbon had 4 electrons and it lost 1 electron, this carbon atom, to bromine, and so it is having only 3 electrons, and these 3 electrons are shared with 3 different hydrogen atoms. So this carbon atom also gets 3 electrons in sharing from 3 different hydrogen atoms. So 3 atoms from sharing it up against, and 3 atoms it is already having of it has its own electron, and so 3 plus 3 6 electrons. So this condition is called sextet, and this another species obtains octet, and this has odd 8 electrons in its valence shell, and so it obtains a negative charge. And the sextet of a structure, and it obtains a positive charge, and this positive charge, and the other species is a valence octet with at least one pair or a negative charge, lone pair or a negative charge. And so this species will have a one which gets the shared pair of electrons, both the electrons of the shared pair obtains a negative charge, and this negative charge also comes with the lone pair. So bromine is having 3 lone pairs overall. If you consider all electrons are in the form of lone pairs, so it has 4 lone pairs because the pairs of electrons are also here. So bromine already was having 7 electrons in its valence shell, and now it obtains 1 electron as in the form from the carbon atom, and so it is 8 electrons, and all these 8 electrons are not forming, taking part in bond formation, so they can be considered as the lone pair. So thus heterolytic cleavage of bromomethane will give CH3 plus and Br minus as we see here in this case. And the CH3 plus has sextet of electron, bromide has octet of electrons, and a species having a carbon atom, as I said, carbon atom possessing a sextet of electrons with only 6 electrons in its valence shell and a positive charge is called carbocation or carbonium ion. For example, this CH3 plus ion is known as methyl cation or methyl carbonium ion or methyl carbocation. This is methyl cation or methyl carbocation or methyl carbonium ion. Carbocations are classified as we have seen this carbocations, and this, as you see here, this is not the final product because the final product cannot be charged species. Usually charged species do not have separate existence, independent existence until unless they are stabilized by other charged particles or a number of charged particles as we see in the case of ionic compounds. So these charged species are there, they will not be stable, so they will go to another step of the reaction or organic reaction. So they will go further move to uh, new states, and thus this is called intermediate. So all the carbocations are usually reaction intermediate. So carbon cations are formed as reaction intermediate. So when I teach reaction intermediate, you should remember that carbocations are also reaction intermediate. So carbocations are classified as primary, secondary, or tertiary carbocations. So these terms are also important. We will see primary carbocation, secondary carbocation, or tertiary carbocations. So what are the definitions of primary, secondary, or tertiary carbocations? We'll just see. So, and what does it means that this is methyl carbocation, and suppose another carbon atom is associated with this carbon atom. In that case, if only one carbon atom is directly linked to the carbon atom having a positive charge, such carbocations are called primary carbocation. And when two carbon atoms are directly linked to the carbon atom having a positive charge are called secondary carbocation, and tertiary carbocation is the carbocation having a carbon atom with positive charge linked to 3 different or 3 alkyl groups. These alkyl groups could be different or the same, and so we get primary, secondary, and tertiary carbocation. If you look at the example, this ethyl carbocation or ethyl cation. In this ethyl cation, this carbon atom contains the positive charge and it is directly linked to another carbon atom, and so this is primary carbocation. So this is primary carbocation. Another example, what we see here, the CH, and as we increase the number of methyl groups to this carbon atom, And what happens? The number of hydrogen atoms will decrease. So what have we done? In the methyl carbocation, one hydrogen we have replaced with the methyl group, so we get ethyl carbocation. Now, if you replace two hydrogen atoms with two different methyl groups, so this group becomes isopropyl, and so this is called isopropyl carbocation. This we know one, two, three carbon atoms are there, and this carbon atom which is having a positive charge over it is directly linked to two different carbon atoms, two CH3 groups, and so this is secondary carbocation. In this example, what do we see? This carbon atom is having one positive charge and it is linked to three different carbon atoms on the three different methyl groups. So it is tertiary carbocation, and this is tertiary carbocation. This is tertiary butyl. The group name is called tertiary butyl carbocation. And how naming of tertiary butyl isopropyl I have already explained earlier in the same chapter. So you can refer those nomenclature as well. This I have explained before. I have explained the IUPAC nomenclature. During actually when I was explaining IUPAC nomenclature or teaching IUPAC nomenclature, I have explained what are the isopropyl or secondary butyl or tertiary butyl groups or isobutyl groups. And there we have also studied neopentyl and so on. Good. So this is tertiary butyl carbocation. So this is tertiary butyl carbocation, this is tertiary carbocation, this is secondary carbocation, this is primary carbocation, and this is methyl carbocation. This one. So carbocations are highly unstable, and why they are highly unstable? Because they have six state of electrons. The carbon atom doesn't have a complete octet. Another thing is it is having a positive charge, and as I have seen, charged species are not stable species, and so these are very unstable species, and they when they if they are unstable species, they are formed for a uh, brief time, for a transient period only during a chemical transformation. So they are reaction intermediates, and since they are reaction intermediate, they are unstable, they are very reactive. They are unstable means they are very reactive and usually formed as a reaction intermediate because they are very unstable and reactive. So they will not be stable. We cannot isolate them. They will form for a brief time, just for a small short period of time during a chemical transformation intermediate, as an intermediate. So alkyl groups directly attached to the positively charged carbon stabilizes the carbocations due to inductive and hyperconjugation effects. So there are two effects that we will study probably in our next class. There are many other effects which are important to understand, which actually gives the stability to organic molecules or organic species, even the intermediates. And one of that effect is called inductive effect, and another is hyperconjugation effect. What are the inductive effects and what is the inductive effect and what is the hyperconjugation effect? This we will study in our next class. Inductive effects could be of two types. Plus I effect we call inductive effect means I effect. So inductive effect could be two types, plus I effect and minus I effect. Plus I effect is electron donating effect and minus I effect is electron withdrawing effect or electron pooling effect. Electron donating effect means electron releasing effect. So methyl groups usually have electron releasing effect. So they can release electrons. So when methyl groups are attached to a carbon atom having a positive charge, so these methyl groups will push certain electron density towards the carbon atom having a positive charge. So they will suppress this positive charge on the carbocation. And so if the number of methyl groups are more, we'll see carbocations will be more stabilized. So in such a case, if you look at the plus I effect, if one methyl group is, if there is no methyl group attached to the carbon atom in a carbocation, that like we have seen in the methyl carbocation, so there will be no stability factor in this carbocation. So then suppose if you add one methyl group, some stability to get some plus I effect. If you replace two hydrogen atoms to add two methyl group, so it will get some more electrons from two different methyl groups. And if you add three methyl groups, you will get even more electrons as plus I effect because all the three methyl groups will work as in, will act as electron donators, and so will get electron density will be suppressed maximum in the case of when the three methyl groups are there, and three methyl groups will reject, when all the three hydrogens of the this methyl carbocation will be replaced with different methyl groups as we see in this case. So because of the plus I effect, we get a stability. Another effect is called the hyperconjugation effect. Hyperconjugation we will study later on, and then we will also see what is conjugation. And hyperconjugation means excessive conjugation. Conjugation we see usually in the case of the pi electrons or usually bound electrons, they are conjugate found in conjugation. When some sigma bonds are also in conjugation with a positive charge or anything, such conjugation are called hyperconjugation. So in this case, what do we see? These CH bonds are sigma bonds, and these sigma bonds can donate its electron density to the vacant p orbital of this carbon. And so since this vacant p orbital of this carbon for even for a transient time, but because of that, this species gets some stability. And if the number of such CH groups because of the addition of methyl groups are more, based on that we can find out the number of hyperconjugative structures. And more the number of hyperconjugative structures, more the stability will the organic species get, particularly the carbocation. So these carbocations, so this is how we obtain the trend in the stability of these carbocations. This tertiary carbocation is most stable, then secondary carbocation, then primary carbocation, then methyl carbocation. Why this is tertiary? Because this carbon atom which is having a positive charge is associated with three different methyl groups or alkyl groups. These CH3 groups could be ethyl groups, they could be propyl groups, any other alkyl group. So if this carbon is with different alkyl group, here they are methyl. This carbon atom having positive charge is linked to two different alkyl groups. This one is linked to only one alkyl group, so primary. This is secondary because two alkyl groups, and this one three alkyl groups. So tertiary, no alkyl group is methyl carbocation, and that is why this is least stable. These carbocations have a trigonal planar shape. So the shape of this carbocation should also be understood. This forms a trigonal planar shape. And why this is having trigonal planar shape? Because it is having lone pair of electrons and only three sigma bonds are there. And this bond, because of the bond pair repulsion, this all the bonds will be arranged in a three-dimensional space so that it can have all the bond pair repulsion will be minimized. And so this we have studied in VSEPR theory, valence shell electron pair repulsion theory. So as per valence shell electron pair repulsion theory, it will form a trigonal planar shape, and trigonal planar shape can also be understood in the form of sp2 hybridization. So the carbon atoms in carbocations are sp2 hybridized. Means all not all the carbon atoms, but the carbon atom which contains the positive charge is sp2 hybridized. Like here in this case, this carbon atom of this methyl group is sp3 hybridized, but this carbon atom is sp2 hybridized, and because it contains a positive charge on it. Right. So this carbocations have a trigonal planar shape with positively charged carbon being sp2 hybridized. Since positively charged carbon being sp2 hybridized, so this carbon atom around this carbon atom, when we consider positively charged carbon atom as a central carbon atom, so it will have the carbocation will have a trigonal planar shape. And this trigonal planar shape you can see here in this case methyl carbocation. This carbon atom and this all the three hydrogen atoms will be in one plane. So if these are suppose this all these three hydrogen atoms are replaced with three methyl groups as we see in the case of tertiary butyl carbocation. So in that case, what will happen? All the carbon atoms, this carbon atom and all the surrounding carbon atoms will be on the plane, and the hydrogen atoms of all the methyl groups will be out of the plane. So the only carbon atom which is linked to this carbon atom, or only the atoms which are linked to this carbon atoms from the constitute this plane, or they contain the corner of this trigonal planar structure or the trigonal structure. The shape of CH3 plus may be considered as being derived from the overlap of three equivalent, and that this is what is explained here. So it is considered that the shape of this carbon atom and methyl considered to derive from the overlap of three equivalent carbon of sp2 hybridized orbitals with one s orbital of each of the three hydrogen atoms. So what we can consider is one p orbital is now empty. So only two p orbitals and one s orbital of the valence shell of the carbon will undergo hybridization. So since only one s orbital and two p orbitals of the carbon in the excited state, each containing one electron, undergo hybridization, so they will form three hybrid orbitals. And so this hybridization, because of one s and involvement of one s and two p orbitals, is called sp2 hybridization. And this, with this kind of things we have already studied in chemical bonding chapter, where we have studied covalent bonding or the hybridization, the valence bond theory. Well, explaining the valence bond theory, I explained it. So now, and these three sp2 hybrid orbitals, they will arrange in the three-dimensional space so that they can have minimum repulsion, because all the three sp2 hybrid orbitals contains one electron, and now this sp2 hybrid orbital share its one electron to one hydrogen atom and so we see the formation of a covalent bond. Now one p orbital which is empty will not take part into the hybridization. This kind of things we already know. So the each bond may be represented as carbon sp2, hydrogen 1 is sigma bond, and these all bonds are since only one bond is there. So these bonds are the sigma bond, and the sigma bond between sp2 hybridized orbital of the carbon, or the having a positive charge, and 1s orbital of the hydrogen, the terminal hydrogen atoms. And so this is the nature of this chemical bond, the sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contains no electron. And since this contains no electron, and this is actually this orbital stays perpendicular to the plane of this molecule. And so this is perpendicular. Suppose another carbon atom is here, and this carbon atom with the hydrogen atom is above in this direction. There can happen overlap between sigma bond and this sigma bond, and that is what we have explained earlier, that is the hyperconjugation. So suppose this was a CH3 group. In the CH3 group, what we see, three different alkyl groups will be there. The three different CH bonds will be there. Sorry, three different CH bonds will be there. One of the CH bond will align in the orientation of this, and if the alignment is proper, in that case what we see the overlap between this sigma, the shared pair of a sigma bond, and this vacant p orbital, and because of that we will see certain stabilization, which is called hyperconjugation. Although the energy difference between this empty orbital and the filled sigma bond orbital is very high, so this overlap will not be much efficient, but it will definitely give certain stability. So each bond may be, and so certain stability we get, but this, because of the hyperconjugation, this species do not becomes very stable, so that it can be isolated. So the heteroclitic cleavage can also give a species in which carbon gets the shared pair of electrons. But as we have seen, the carbon in this case gets a positive charge. It doesn't get the shared pair of electrons. Shared pair of electrons goes to some more electronegativity than some other atom. However, what can happen if an organic molecule is there and in which the shared pair of electron is shifted towards the carbon, means the carbon is more electronegative atom than the atom it is bound to, then the shared pair of electron will be shifted towards the carbon, and since the shared pair of electrons are shifted towards the carbon in the heterolytic cleavage, these electrons will be shifted to the carbon, and so carbon will attain a negative charge, and such species are called carbanion. So a carbon species carrying a negative charge. So heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. And if carbon gets the shared pair of electrons, a carbanion is formed. A carbon species is formed with a negative charge, and such species are called carbanions. For example, when a group Z, this is just an hypothetical example, attached to the carbon leaves it without electron pair, the methyl anion is formed. So this CH3 is there in Z group. So this Z group having lower electronegativity than this carbon, then in that case, in the heterolytic cleavage, this electron shared pair of electron will shift towards the carbon atom, so the carbanion will be formed. So another way, the representation of this heterolytic cleavage is this. I forgot to explain you. It to represent this, we use a curved arrow, and in the curved arrow, we show this curved arrow. We start this curved arrow. The tail of this curved arrow start at the middle of this bond and it ends at the more electronegative atom. So here it starts, this arrow starts at the middle of this carbon bromine bond and it moves towards the bromine, moves towards the bromine and it ends at the bromine because bromine is more electronegative. In this case, since Z, this G group is having lower electronegativity, as I said, because we have also seen organometallic compounds. Means the carbon is bound to a metal atom like organolithium, even the Grignard reagent, CH3MgX. So carbon is bound to a metal. In such case, in all the organocombined organolithium, we see carbon and metal bonds, and we know electronegativity of metals are less than the electronegativity of the carbon. And so, if those bonds are broken, suppose lithium and carbon bond is broken, then in that case, what we'll see, the negative charge will appear on the carbon atom, and thus a carbon ion will be formed because the carbon atom is more negative than the metal lithium. Similarly, in Grignard reagent, we see the formation of carbon ion. And those carbon ions are also reactive intermediates because they are also having negative charge. And so the charge species are, since they are not stable, so they will be formed only as a reaction intermediate for a very transient period of time and they will then be consumed in the next step of the reaction. So they will consumed in the next step of the reaction to form another intermediate or maybe the final product, depending on the how many steps of the reaction are still to happen or the pending at the step where the carbon ion or the carbocations are formed as an intermediate. So what do we see? This Z group again here in this case, what we have seen, we have used a curved arrow to show the heterolytic cleavage, and this curved arrow, in this curved arrow, we also started at the middle of this carbon G bond, and it ends at the carbon atom because this carbon atom is more electronegativity in this case. So this CH3, this minus group is formed. The methyl carbon ion is formed Z plus usually is metal. So carbon in carbon ion is sp3 hybridized. In this case, what do we see? This carbon atom is having complete octet. This atom's octet will not be complete, and anyway, it is a metal. So metal have electropositive character. So this carbon atom has its complete octet. Why? Because this carbon had 4 electrons, 3 electrons it obtains in sharing from 3 different hydrogen atoms, and 1 electron it actually accepts or gets from this Z of this Z atom. So it is having negative charge, one net negative charge, and so it is having 8 electrons. So 3 electrons from hydrogen, 1 electron as a negative charge, 4 atoms, 4 electrons it already had in its valence shell, so octet of this carbon is complete. So carbon in carbon ions, since the octet of this carbon is complete, so another thing that we can see here is this carbon is having 3 sigma bonds with CH sigma bonds. The 3 CH bonds are there. All these bonds are sigma bonds, and it also has a lone pair because 1 electron of this carbon atom itself is not taking part in bonding, and 1 electron is obtained as an extra electron from this Z atom in the heterolytic cleavage, and so it will have. That's why it obtained a negative charge. So it is having 2 electrons as a lone pair. Now these 2 electrons are also considered to be in hybridization, as I have explained earlier. The number of sigma bonds and the lone pairs will tell you what will be the hybridization of the central atom. So since this carbon atom contains 3 sigma bonds and one lone pair, so its hybridization will be sp3 hybridized. So if this is sp3 hybridized, and if the sp3 hybridized and means what should have the geometry of this carbon atom, the geometry of this carbon atom will be tetrahedral. But what we have seen, one of the positions of this tetrahedral symmetry is occupied by the lone pair, and these lone pairs are part of this carbon atom. So in defining the shape of this carbon ion, we will not consider the lone pair. So this will be the pyramidal structure. It will form the pyramidal structure as we see in the case of ammonia. And so this carbon ion, methyl carbon ion, if you look at it, is also isoelectronic with ammonia. So this methyl carbon ion is isoelectronic with ammonia. Its shape is also similar to the same to the shape of the ammonia. And so this ammonia, this carbon atom is having, as you see, the 7 electrons. Nitrogen also has 7 electrons. Nitrogen also has seven NH, three NH bonds, and carbon is also having three CH bonds. And nitrogen had one lone pair, and carbon is also here a lone pair. So the shape of the methyl carbon ion is same that we obtained for the ammonia, the pyramidal shape. That of the when we see the methyl carbocation, the shape of this is similar to that of the BH3 molecule. The BH3 molecule, and BH3 molecule is also a six-state boron, has a six state, so it is triboron planar, the BH3, and this BH3 has six state, as we see it doesn't it is not stable into the monomeric form, so it forms dimer, the things we know, and the dimer formation is because of the sextet of electron. But if you look at the number of electrons in CH3 plus and BH3 in the monomeric form, you will see those they both are having same number of electrons, same number of total electrons, same number of valence electrons, so they are isoelectronic, isostructure as well. So they have isostructure, same structure, isostructural, isoelectronic, same number of electrons, total electrons that we found. So, carbon ions are also unstable reactive species, and why they are reactive species? Because of the presence of a charge, negative charge on it. So, they are unstable species, and they are formed as an intermediate and generally produced as a reaction intermediate. The organic reactions that proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reactions. So the organic reactions in which heterolytic cleavage happens, those reactions are called ionic reactions. So remember, ionic reactions, if you study in organic chemistry, it means this is reaction involves heterolytic cleavage of certain species. Or such reactions are also called heteropolar reactions or simply the polar reactions. And why the polar reactions? Because we see there is already pole in this bond and two different poles are further formed because of the heterolytic cleavage. And this starts with because of the polar nature of this bond mostly. Now, so it is not necessary that if the polar bond is there, it will always undergo a heterolytic cleavage. Heterolytic cleavage, whether it will undergo heterolytic cleavage or not, it will also depend on the reaction conditions. Means under what conditions this organic molecule or a chemical substance is kept in. So the organic reactions that proceed through heterolytic bond cleavage that I have already said, they are called ionic reaction or heteropolar reaction or the polar reaction. It is promoted by, so this heterolytic cleavage is promoted by the difference in electronegativity. If there is a difference in electronegativity, there is a chance between the bonded bounded atoms, then there is a high chance that it will undergo heterolytic cleavage. If the difference in electronegativity will be is large, then there is a higher chance of this reagent to undergo a heterolytic cleavage. So this is also a difference in electronegativity actually enhances the possibility for the heterolytic cleavage. Another thing is the presence of polar solvents. So polar solvents, what does it do? It stabilizes polar species. The polar solvent will stabilize polar species. So once this polar species is the product of this particular state is stable, the product stability increases, means that this reaction will move forward more in the to a larger extent in the forward direction, and these steps are not in the one state. These are actually this is the reaction steps are in equilibrium. So reactions are in equilibrium with the product. So this extent this reaction will go to a larger extent if the polar solvent is there because the product is stable is more stabilized, the charged species are more stabilized in the polar solvent. And then this is absence of sunlight. Usually, if the sunlight promotes the homolytic cleavage. If the sunlight is not there, so the chance of heterolytic cleavage is more. And not only the sunlight, also if there is a high heat, if you are performing a reaction under a heating condition, if there is a very high heat and under a sealed tube, there is chance that the reaction will undergo means this cleavage will be the heterolytic cleavage. So the substance will undergo heterolytic cleavage. And let us now study the homolytic cleavage. So heterolytic cleavage, we have already seen homolytic cleavage. Also, I have defined both the shared pair of electron will go to the both the atoms which are uh, uh, which form this chemical bond on which have shared its electron. So two atoms sharing its electron forming this covalent bond, and now these two electrons will go one electron out of two electrons shared pair of electrons. One electron will go to each atom. And then the such cleavage are called homolytic cleavage. So each bonded atom departs with one electron of the shared pair. So cleavage means two a bond is broken, two species are being separated, and if the two species being separated and the gain one electron each, then the such cleavage is called the homolytic cleavage. The single electron movement is shown by half-headed or the fish hook curved arrow. This is called fish hook, and this fish hook, the curved arrow, it is represented as. So this is a half-headed curved arrow. One can say half-headed curved arrow, full arrow, heterolytic cleavage, half-headed curved arrow, which are also called fish hook. Means it is this particular bond is undergoing homolytic cleavage. And this we use two half-headed curved arrow. One goes in this direction and another goes in another direction. So homolytic cleavage results in the formation of neutral species, and this neutral species could be atom or group, and that contains an unpaired of electrons which are called free radicals. So the atomic species free atoms or the group having one odd pair of electrons are called free radicals. And we see the example a bit later. So what I have said is, suppose this Rx bond is to be broken. So in that case, what we have seen, both the electrons means of the shared pair are shared between are given, each one electron is given to two different species, and so we use arrow, curved arrow, showing one electron means half of the electrons that are there all in this bond is going in one direction, and half of the total electrons will go in another direction. It simply means one electron is going towards this atom and one electron is going to this atom, and this half curved arrow of the fifth hook starts at the middle of the bond and it ends at the either atom. So like carbocations and carbon ions, free radicals are also very reactive species. So these species are having, though they do not have charge on it, but they have odd pair of electrons. Their octet is not complete, and so they are also very reactive. They are obtained as a reaction intermediate because they are having incomplete octet, and any species having incomplete octet is not stable. This is what we already know from our understanding of chemical bonding. So hemolytic cleavage can be shown as this. So one electron goes to this R, one electron goes to this X, and you can see this is CX bond. X is halogen, usually halogen atom, and there is a difference in electronegativity. But in the presence of sunlight or the high heat, it undergoes homolytic cleavage. So what I said earlier, the heterolytic cleavage is promoted by absence of sunlight or the absence of peroxide catalyst or the absence of high heat. So presence of high heat or sunlight promotes homolytic cleavage even of the bond which is polar, or also the presence of peroxide catalyst as well. It promotes the homolytic cleavage because peroxide bond, O bond, there is no difference in electronegativity. It will itself form two peroxide radicals, and these peroxide radicals will further breaks these bonds, and so it will create another radical, so that it will actually peroxide radicals presence or the formation of peroxide radicals from the peroxides um, promotes the homolytic cleavage of a substrate. So homolytic cleavage can be shown as this. Alkyl radicals are classified as primary, secondary or tertiary as well. So this I forgot to explain here for the stability of the carbon ions. So I'll explain. Let us firstly, like we have seen the primary, secondary and tertiary carbocation. Similarly, we can also have primary, secondary and tertiary free radicals as well, and the stability of the primary, secondary and tertiary free radicals follow the same trend that we have seen for the carbocations. So the tertiary free radical will be most stable, then the secondary free radical, then the primary free radical, and then the least stable is the methyl free radical. So alkyl radicals are classified as primary, secondary or tertiary, and tertiary means this radical atom containing a carbon atom containing odd pair of electron is bound to three alkyl groups, and the carbon atom containing odd electron, if it is bound to two alkyl groups, then this becomes secondary. If it is bound to only one alkyl group, primary and no alkyl group, this is methyl free radical. So alkyl radicals stability increases as we proceed from primary to tertiary, like we have seen in the case of carbocation as well. So the carbocation stability of the carbocation and the free radicals follow the same trend. Tertiary is most stable. Then comes the secondary carbocation or free radical. Then comes the primary carbocation or primary free radical. Then comes the methyl carbocation or methyl free radical. Organic reactions that proceed by homolytic fission. This cleavage are also called fission, means the breaking that you know. So free fission, fission is it also means cleavage, the breaking of a bond, are called free radical reactions. So the organic reactions that proceed by a formation of free radicals are called free radical reaction or homopolar reaction or non-polar reaction. So they are also called non-polar reactions because or the homopolar reaction. Homolytic cleavage is promoted by non-polar solvent. So non-polar solvent is there. So this charge species will not be stabilized in non-polar solvent. So the charge species like carbocation, carbon ion will not be preferred in non-polar solvent. And then the presence of peroxide catalyst, as I explained, peroxide catalyst or peroxide itself undergo heterolytic cleavage very easily and to sorry homolytic cleavage very easily, and so it will form two different radicals based on the oxygen or pair of electrons will be in the oxygen. Like suppose HOHO, hydrogen peroxide, it will form two OH free radicals or ROOH. So alkyl substituent of alkyl substituents of this hydrogen peroxide. So they will also form two RO radicals, and these radicals will now go abstract one electron from this shared pair of electrons, and so it will form another radical based on this, or maybe this free radical can combine with this X group, and so that the formation of Rx will happen, and then sorry, not alkyl radical. This suppose OH radical or RO radical are formed that RO radical can combine with this S group, it will form ROX, and then there is a formation of another R radical. So R radical is, and those it means it is promoting the homolytic cleavage of this bond, and so the radical free radicals are formed. Also, the peroxide of presence of peroxide or peroxide catalyst or the presence of sunlight, as we have seen here, or presence of very high heat promotes the homolytic cleavage. So these conditions are important. How will you know that a homolytic means that in which reactions the carbocation or carbon ion will be formed as intermediate and what reactions the free radicals will be formed? To understand that, you have to understand in what are the conditions under which homolytic or heteroclitic cleavage will of a chemical of an organic molecule will happen. Any conditions which favors the homolytic cleavage, free radicals will be formed as intermediate, and the conditions which favors the heterolytic cleavage, carbocations or carbon ions will be be formed as intermediates. Then let us now talk about the stability of the carbon ions, which I forgot to mention here. I also mentioned. So, if, as we have seen the primary, secondary, and tertiary carbocation, primary, secondary, and tertiary free radicals. Similarly, we can also have primary, secondary, and tertiary carbon ions. And what we have seen if the alkyl group is attached to a carbon ion, if the alkyl group is attached, since it has electron donating effect, so it will increase the electron density at the carbon atom, which already contains a negative charge. So since it will increase the electron density at the carbon atom, so charge at the carbon atom, negative charge at the carbon atom will further intensify. And if the charge gets intensified, it means this carbon ion will be less stable, it will be more reactive because the more charge accumulation is not a favorable condition energetically. And so if more methyl groups are added, so the stability will further decrease. So the trend that we obtain for the this carbon ions, stability of the carbon ion is what is to follow this trend. And let me just try to adjust it somewhere here. The stability order will be stability order of carbanions will be methyl carbon ion, more stable than primary carbon ion, and primary carbon ion is more stable than secondary carbon ion, which is more stable than tertiary carbon ion. And the examples you can see, the form of structure, that is not right, carbon ion in this case, it will go to. And so I have added it here. So the carbon ion, methyl carbon ion is most stable, then the primary carbon ion, the secondary carbon ion, the least stable is tertiary carbon ion, because three alkyl groups are there to donate electrons to the carbon atom which already contain one electron, and they are negative, which means a negative extra electron, one extra electron is one negative charge, and so its stability will decrease. If you attach one electron withdrawing group to a carbon ion, so that electron withdrawing group will stabilize the carbon ion. So in that case, carbon ion will get stabilized. And if you attach an electron withdrawing group to a carbocation, if you attach electron withdrawing group to a carbocation, it means it will pull some electron density even from this carbon atom, so the stability of that carbocation will decrease. So if you look at the primary, secondary, and tertiary carbocation carbon ion, so this there will, instead of this positive charge, there will be negative charge at the carbon atom, and if the negative charge will be there, the sign of this sign will be this form. If there are three negative charges on it, so the sign will change. A sign will change. So let us actually take this example. We'll just change the sign in this case. Instead of writing primary, secondary, or tertiary, and this term is anyway clear to you, and negative charge and negative charge on this as well. And now we will change the sign. This is more stable. Then comes this primary carbon ion, and then comes the secondary carbon ion, and lastly the tertiary carbon ion. Now the time is over. I'll stop here. We'll see other important points like this thing in our next class. Okay.